Hi guys, Godwin here. I made this video just to try my hand at one of the surprises, the surprises that my batch and I have received over this first week of classes. Kasi one of our majors is vibration engineering, VIBEENG. And it turns out that our prof there is Sir Jerry, who is known to throw massive curveballs at the first days of class. So in our orientation of this subject, he told us to read like the first three chapters at our first three sections of the book that he was recommending. And then, so I did read somehow. And then he throws this he throws this concept at us at the very first day. So it's called the Lagrangian. It's more used now in systems. So basically, systems are just like a bunch of things that move around, right? Uh, Yun, systems with multiple degrees of freedom, more than one, kumbaga. So, one degree of freedom that's like a pendulum that's swinging like back and forth, or like a spring that's moving something without friction, of course, back and forth. And yun nga, they only have 1 degree of freedom because they're only allowed to go in that direction, right? And so for Lagrangians that are used more for kapag there are two pendulums like a one on top of the other, or like a spring and a pendulum. So ayun, he threw us this curveball and we were all baffled and shocked and confused and scared. But I'm gonna post this video as my attempt at understanding what the Lagrangian is. So let me introduce you to the Lagrangian. I write it with a fancy L, although I think many other people just write it with a normal L. So L, the Lagrangian, is just equal to T minus, okay, I'll just put some space, ayan, T minus V. So you might be asking, what's T and V? Okay, so the Lagrangian has units of energy, right? And so this T and V, the T is actually our kinetic energy. And V, surprisingly, is our potential energy. And so you might ask, like, preliminarily, why is it T now? Why is it V now? So yung T daw, the T for kinetic energy, kinetic energy can be equated to work. And so people think that the T comes from the French word for work, which is travail. Travail. I don't know if that's the correct pronunciation, but anyway, so that's where the T came from. And then for the V, it's less clear now. There are two theories. Kasi the one who first used a different letter for potential energy was William Rankine. And then he made it U, right? U. So the U is for internal energy that can also be equated to potential energy, right? And so, ang ginawa naman, I think it became V daw because it was close to U, the letter U. And then, there's this other theory that ginawa siyang V because, potential energy can also be electrical potential, which is voltage. So, ayun, it's either voltage or it's near you. Or near you. Anyway, I left this space because I'm gonna clarify that the potential energy is a function of two coordinates, while V is only a function of one coordinate. And so I'm gonna introduce you because when I write this down, Q and then Q dot, and then Q lang dito. That's kind of weird. Like, what's Q? Is that heat flux? No, this is what we call Q is what we call a generalized coordinate. Right? So, let's just consider like a pendulum. Ito yung equilibrium point niya. It's going like that, right? So, let's say preliminarily, we also just choose two variables. Sabihin natin, the x-axis is there, going in that direction, and then the y-axis is going down. And so you might be tempted to get the relationships for for x and y as a function of t, right? But we realize that there's a simpler version of this because we know that if we consider, ayan, if you consider this triangle right here, we know that x squared plus y squared is equal to L squared. That's the length of the pendulum wire. Anyway, but there's also another way to, what do you call this, to relate these two terms together, which is this angle right here, which is theta, right? So this now becomes, ano tawag dito? X is now L sine of theta, and then y is now L cosine of theta, right? And so this is not generalized. These are not generalized coordinates because they are related to one another to using theta, which is the generalized coordinate. Kasi it dictates both x and y, right? From this you can create the other coordinates, and so that's what we're doing here. We don't want to put their position or rotation. We're just gonna generalize it. Kaya nga generalized coordinates. So the q dot naman, there's a dot on top because that's shorthand na for time derivative, right? And ayun, so we know that kinetic energy, one of the most known formulas in science, is just 1/2 mass times velocity squared, right? And we know that velocity is just a time derivative of the mass, right? And so if it's a function of velocity, right, of q dot, kumbaga, it should also be a function of, what do you call this? It should also be a function of position, right? Since it's just a time derivative of position. And so, okay, that's how we come to the intuition that T is a function of both Q and Q dot. And so for V naman, of course that's just potential energy. What's the the elementary formula for potential energy? That is mgh, right? H is a function, ano tawag dito? It's just a function of position, right? It's how high are you from the ground, right? And so ayun, that's how we got to the point that potential energy is just a function of Q, okay? So after that, you might be asking, okay, sige, I'll accept that Lagrangian is T minus V, but why is it T minus V? In my mind, kasi when I first saw what the Lagrangian was, I was like, isn't this stupid? Because you shouldn't be computing this. You should instead be computing for what T plus V is. Oh, oops. Okay, I'm stuck again. Okay. You should be computing for what T plus V is, since we know this is the total energy, and we know that this is always conserved because ano tawag dito? Conservation of energy. But this is actually a sibling of the Lagrangian called the Hamiltonian, which I think will mention Hamilton's name again. This is not the Alexander Hamilton. Pero basically, they're related in the sense that I read this article kasi yesterday. It's Science Meets Fiction. It's Alex Howe's blog website about why the Lagrangian equals T minus V, and basically he found this answer by on Stack Exchange by unassumingly meek, and he has this graph. This is the motion daw of a pendulum as it swings back and forth, and so we'll just remember this. We see that the Hamiltonian, the green line, is always constant, which is, it checks out with our intuition because conservation of energy, right? There's no external forces. There's no external energy that is put into the system or is removed, right? Kasi, okay, we're assuming that there's no friction in the air, whatever. But the Lagrangian has this sinusoidal shape. So that's what we'll be discussing. We'll just draw. Actually, pwedeng mag-base na tayo dito, right? Okay, let's draw the pendulum again. Let's make it bigger. Ayan. Ayan, okay. Ayan. So we let it go. Okay, imagine that's my hand. It's a horrible hand. Anyway, we let go at this point. And of course, at this point, the ball isn't moving. The pendulum bob isn't moving, right? So of course, its velocity is 0. And so its kinetic energy must be minimum, which is 0, right? But this is where the pendulum is at its highest point, Kasi kumpara mo dito, let's just say that this is our z equals 0, kumbaga. This is definitely higher, and it can't go higher from here, right? Because, you know, that would require you to put more energy, which bonks up the system, kumbaga. Sorry. Yeah. So the potential energy of this is at its highest, max, which is mgh, assuming this is our h. Yeah, this is our h. Anyway, once it reaches this lowest point, the potential energy is mgh, but our h here is 0. So it reaches a minimum at 0, of course. And of course, at the lowest point, this is where the velocity is at a maximum. This is where the pendulum is fastest. So of course, this is 1/2 mass times velocity max squared. Ayan. So that's why the Lagrangian here, anong tawag dito? That's why it periodically goes up and down. Kasi the Lagrangian, if you think about it, is how much the energy changes from one state to the other, right? At this state, lahat ng energy, at the initial state, lahat ng energy natin is all potential. And if you see here, it's T minus V. Of course, if walang T, 0 minus V everywhere, which is all of the energy that we have, of course it's going to be negative, no? And at the lowest point, of course, there's no potential energy now, but all of the energy is converted into kinetic energy. So all of the energy minus 0, of course, you're gonna reach the maximum, right? And so that's our intuition for how the Hamiltonian and the Lagrangian are related and how the Lagrangian is important. So I won't mention the Hamiltonian now because that's like way out of my scope for the things that I needed to read up on for this video. But anyway, another dumber option for answering why the Lagrangian is T minus V is it just so happens to be the solution for the Euler-Lagrange equation, which is the main goal for this video. You can see that this is part 1. This is gonna be a 2-parter series because the Lagrangian is so new for us third years na kailangan natin ng more than just one video for that. Anyway, so what Sir Jerry did was he derived the Euler-Lagrange equation from an already known principle known as Hamilton's principle. So just write that down. And so we'll start actually the derivation right now. Hamilton's principle. Okay, Hamilton's principle. All right. Okay. In order to prove that indeed the Lagrangian T minus V is one of the solutions for the Hamilton's principle, we're going to use that as a solution, as a substitution. So we'll call this equation 1 for the Hamilton's principle, which I'm going to call as equation 2. So ito yung Hamilton's principle. So delta here means small steps, right? Just like dt, just like the big delta t, the triangle, that mentions small steps, right? So this is supposed to be the Lagrangian dt, right? The t's here, they mention time. Okay, so I'm going to I'm going to put in the t minus v here, t minus v dt plus, okay, so this is actually the part of the equation that's more important for us. Kasi this one is when we introduce external forces into the system. From T1 to T2, we have small steps in non-conservative work, dt. That should be equal to 0. In most cases, kapag wala kang nilalagay na external forces or you're not taking out any energy, this is supposed to be 0 normally. But anyway, we'll just include that just for posterity. And then what we're gonna do next is we're going to put this delta inside, and then inside the integral, and then we'll expand from there. So I'll just do that. From t1 to t2, we'll do delta of t minus v dt plus integral from t1 to t2 of small steps of non-conservative work with respect to time. Okay, ayan. And so what does this mean, the delta t minus v? What does that mean? So if you recall in, I think that was Kaleng 1. Yeah. Differential calculus. If you recall in the last portions of DiffCal, there's this portion with partial derivatives where kapag pinapahanap yung small steps of a function that has many variables, you're going to split it into its partial derivatives. So that's what we're going to do now. So I mentioned kanina na the kinetic energy is a function of our generalized coordinate and the time derivative of that generalized coordinate. So I'm going to split that in two, and then itong potential energy, it only has one variable, so I'm just going to differentiate that with respect to its generalized coordinate. So I'll just do that now. Okay, so T1, T2. Oh, of course, we're addressing the elephant in the room right now. These integrals are going to combine soon because they have the same upper and lower bounds. Okay, anyway, so we're gonna have a big parenthesis, and then we're gonna write down, unahin muna natin i-derive yung t with respect to q dot. So partial derivative of t with respect to q dot. Okay, I wrote down here qi pala because, as I mentioned before, this works better for systems with multiple degrees of freedom. So I'm writing the qi because mamaya meron tayong q1, q2, q3, right? Just for generalization. And then we're gonna write down here yung delta natin. Delta qi dot, right? So they cancel out and you're left with the partial t. And then we do the same with respect now just to q. And then delta qi, no more dots kasi nga it's just qi, right? Minus the v, partial of v with respect to qi again, and then you have the delta qi again. And then dt, and then plus the same thing for this one. And now we're going to go on a tangent just so we can expand this and then combine these two integrals together. So yung yung non-conservative work natin, non-conservative work, if you recall the most basic work formula we have, it's force times distance, right? And so for now, we're going to we're going to treat this distance as just, what do you call this? As just a generalized coordinate, right? Another thing for work is that it's just the same as moment times angle, right? Yeah, it's the same thing, no? And so, you can both point this to the generalized coordinate small q, right? So if you have a bunch of non-conservative forces, right? We're gonna call it big Q, which is very confusing. This can either be force or moment, depending on what your generalized coordinate is, right? Depending if it's translational, if it's x, you're gonna put this in force. If this is rotational, if your generalized coordinate is theta, it's rotational, you're gonna make this moment. But either way, it's just the force, anong tawag dito ni sir? The forcing equations, I think. Yeah, the forcing equations, and then multiplied by the generalized coordinate. And then you sum them all up together. But for the sake of simplicity, sabihin lang natin na we're going to have only one external force. So we'll just say that it's big qi times small qi. And so for small steps of our non-conservative work, we can just say that it's big qi times delta of small qi. And so we're going to label this as equation 3, and then we're going to substitute that here, which is, I forgot, is our equation 2. All right, anyway, I should also combine them na since save space. From T1 to T2, we're just going to copy all of this first. Qi dot times dqi dot plus partial T partial Qi delta Qi minus partial V partial Qi times delta Qi plus, right? Plus we have this big Qi times delta Qi dt is equal to 0. And so we're gonna have a nice moment here where almost everything, or almost every term here has delta Qi, except for this one, which is delta Qi dot, unfortunately. And Sir did something about this. He brought this part of the integral out so that he can compute it using, sadly, integration via parts. So I'll just bring this out. Partial T over partial Qi dot times dqi dot dt. And so he said na it's going to be in the fashion of uv minus integral of, minus integral of v du. And so, okay, I'll make this number 4, I think, yeah, equation number 4. And then we're going to substitute that back to equation number 2. And so, the problem is now we're going to have to pick what u is and what dv is, because this is supposed to be in the term of u dv. So, why not? Yung nasa tapat na ng u at nasa tapat na ng dv ko, yun na yung pipiliin ko. So, let's say that u is equal to partial t over partial qi dot. So, what's going to be our du? Well, how are we going to differentiate this? Of course, the integral we have is related to time. So, we're just going to derive this with respect to time. Since wala naman ditong, anong tawag dito? Wala ditong variable related to time, we're just going to have the time derivative here. And then we're going to continue with that. Just like that. And then we're just going to add the dt. Okay, so that's our du, right? Okay, dv naman, of course, it's just delta qi dot dt. So this is saying, this is just the same as, kumbaga, how do we say the same as? Same as, kind of like dqi over dt, right? Partial of qi over dt, right? Since it's just a time derivative, right? So if you integrate that, integrate both sides with respect to t, you're gonna get v is just magically delta qi, right? Since it cancels, right? Okay, and so now you have our u, our du, our dv, and our v. And so we're gonna equate that here. U times v is, where is that? Ito. Oops. Partial t over partial qi, and then delta qi, and then from time 1 to time 2, minus, this is minus, right? Integral from t1 to t2, t1 to t2, of v du, v, this thing, may ako na isulat before the end, time derivative of, partial derivative of kinetic energy with respect to velocity, and then isulat ka na to, and then dt, right? And so for this one, for this first term, you're gonna notice na wala siyang time variable actually. So this is just literally a constant, right? So if you integrate a constant, ano tawag dito? If you substitute something that, if you substitute a variable to something that's constant, walang mangyayari. So it's just this constant minus this constant, it just cancels out, right? And so, finally, we have the simplification for equation 4, which we're going to substitute now here to this part. We're going to have from time 1 to time 2, we're going to have minus, this is minus, time derivative of the partial derivative of kinetic energy with respect to velocity. So now it's delta qi. So everything here is delta qi. And then we'll just repeat the other terms. So partial v partial qi times delta qi plus big qi, that's the forcing equations, times delta qi dt is equal to 0. Okay, so now the good thing about this is these times are just arbitrary, right? So it just describes from one point of time to another ano yung magiging result, right? So we can also cancel that out, since we can just if we derive all of this, it's just gonna be it's just gonna be all of this blah blah blah, and then from t1 to t2, and then after that you're gonna have all of this blah blah blah, blah, and then times t2 minus t1, right? So you can cancel that because the other side is just 0. So wala rin, right? Anyway, oh my goodness. Okay, I might just erase now. Anyway, so that's I think that's Sir Jerry's justification of removing the integral. And then we notice now that every term here has the delta qi, which we can peacefully cancel. And then finally, well, second to the last step, we have this. We have this beautiful result plus partial t over partial qi minus partial v over partial qi plus qi. So I think Sir's last step is to just transpose these three onto the other side and then flip the equation over. So it becomes the time derivative of the partial derivative of kinetic energy with respect to velocity minus partial derivative of kinetic energy with respect to our generalized coordinate plus our partial derivative of potential energy with respect to our generalized coordinate is equal to our qi. So this is the Euler-Lagrange equation. Oops, Lagrange equation. So this is the magical equation that we're gonna use for the next part of the video, where we're going to test out how this fares when it comes to three systems. The first one is just a spring system without friction pa tayo. So just a spring, and then a pendulum with low enough angles, small enough angles, kumbaga, and then a doozy, which is a pendulum with a spring attached to it. And then we'll see the magic of the Euler-Lagrange equation. So I'll see you there, hopefully. Please keep learning. This is a really hard topic. I want us to all pass VIBEENG. Bye, guys.